And you might think, okay, Emilia, that's all well and good, but why would I need to know this? Because coordination compounds have a huge importance in life, and the environment. And the next slides are about this, about typical examples of compounds that either you can find in nature, or this one we have made ourselves, that are important for our everyday life and important for our health. And as I will see in a later slide, are important because without coordination compounds we would not be alive. Literally, we would not be breathing. So the first example I want to bring here is still one of the best known and one of the best working pharmaceutical drugs we have to fight cancer cells, to fight cancer, and that's the compound cisplatin. So here you've got the platinum surrounded by two chlorine atoms, so two chlorides, and two ammonia molecules, and the cis refers to the fact that you have the two ammonia pointing towards the same side of the molecule and the two chlorides towards the other side of the molecule, rather than have them, for example, one ammonia here and one here across each other. And again, it's one of the, it's a very well established anti-cancer drug. We will see that coordination compounds is a great way that the body and the environment has to deal with metal ions. We need metal ions in our life. We need them for all sorts of things. If nothing else, we need them because they are excellent at holding electrons and giving electrons away. They handle electrons really well because they can accept and donate electrons. They're very useful, and we will look into it in future videos. However, they are not particularly life friendly or environmentally friendly. We cannot cope with the metals as such. So this is a way that we have, and the body has, the nature has, to encapsulate those metal ions that we need into a structure, and I will show you in future slides that sometimes it's an organic structure, so it's made of carbon and hydrogens, and allows that metal ion to get into the environment, to get into our bodies and do its function without being a health hazard. The example I'm bringing here is a chlorophyll, one of them, in this case alpha, they all have, which has, if you can see here, it has this magnesium ion, and this magnesium ion is surrounded by 4 nitrogen atoms, and they all have their electrons that are donating to the orbitals of the magnesium, that is able of accepting them and forming that bond. And this is an example of what we call a polydentate ligand. And that means that you have more than one, the atoms that you have coordinated to your metal ion come from the same ligand. We also call them chelates or chelating ligand. Apparently for ancient Greek, and chelate comes from crab. So you can have a monodentate ligand, and it is when it can only make one bond. So let's say here there is some sort of metal ion, you have your nitrogen, and it only can make one bond. But if you have a molecule that has more than one nitrogen, or a nitrogen and an oxygen, more than one atom that can donate electrons, and they are attached, then when you have a polydentate ligand, it can sink its teeth on the metal ion in more than one place. And the one you've got there with all those nitrogens around is called a porphyrin ring. More examples of compounds in which you have this coordinative bond, more coordination compounds in the sort of environmental and life sciences. Vitamin B12, you've got here your cobalt ion, and it's surrounded by 5 nitrogens. 4 of them are in the ring, and they are donated by a polydentate ligand, and then you have a third position, which is here. Actually, this is a carbon here, which is that extra position that is occupied by that nitrile group. And again, we're thinking this is a vitamin, so we're looking how you can put a metal ion in a, this is an organic compound. It's also it's all made mostly of carbons and hydrogens with the odd oxygen and the odd nitrogen. So that's another example of how you can have a metal ion in an environmentally and health important compound. And my last attempt to try to convince you that coordination compounds are fundamental in environmental and life sciences. And it is that if the pharmaceutical drug hasn't convinced you, or perhaps the fact that chlorophyll is a coordination compound hasn't convinced you, and don't particularly care about vitamin B12, I'm sure you will all care about breathing, because we all need to breathe to survive. Well, hemoglobin, our good friend protein hemoglobin, that helps us to, trap oxygen from the air, put it into our lungs, pick up the carbon monoxide and chuck it out. It has what we call it's quite a complicated structure. It has two fragments, so it's a four fragment structure, and it has what we call 4 heme groups, which are here highlighted in green in this picture. Let me draw them 1 second. And if we zoom into these heme groups on the right, you will see that, again, that's an organic compound. You may not be able to see it, but there are carbons all around here. More about this if you don't know it. When we talk about organic chemistry. And the key point, it has an iron with 2 positive charges in the center of that heme group, surrounded by 4 nitrogens. So again, this is an example of polydentate ligands. They tend to be more stable if you have an atom encapsulated. So if you have a metal ion encapsulated in a polydentate group, it's in a polydentate ligand that's more stable, that have the same metal ion surrounded by those atoms, but independently, so not attached to each other. So polydentate ligands are more stable than monodentate ones, and that's why they normally are preferring in compounds that have biological importance. So you've got here the heme group, and you have 4 of them in your molecule of hemoglobin, and that's that iron. It's that iron that will attach to the oxygen. Is that by forming another coordination bond. Is that iron that will liberate the oxygen and then will accept the carbon monoxide and get it out of our bodies. So again, another example of how a coordination compound is fundamental in life sciences. So this is all from me. We have covered a lot, because in this series of videos we have looked at the basic types of bonds that you can have. Ionic, when electrons are exchanged and one atom becomes positively charged and the other negative charge. Metallic bonding, which is what happens between the bonds between metals, and how that means that electrons are pooled. There's a pool of electrons that are being shared by all those atoms of metal. And the most important, maybe not most important, they're all important, but most common type of bond, which is covalent bonding, in which you have a sharing of electrons. So 1 electron from each atom that forms the bond. And a specific type of covalent bonding called coordination bonds, in which there is a sharing of electrons, but with more than one of the atoms, a metal ion, will donate orbitals of low enough energy, and the other atom that we call the ligand will donate the 2 electrons. And how that has a huge importance, and loads of pharmaceutical drugs and loads of compounds of environmental and life science importance are coordination compounds. And that's what I wanted to introduce this here, so you're aware of that way of making bonds, which is go beyond the sharing or electrons, or donating electrons, or pooling electrons. So I hope it was useful. If you have any questions, as usual, just drop me an email, and thank you for watching.